Yeah, let me share the screen. By the way, guys, I'm gonna write on here, and you should be able to like write on the top of my writing. So like, if at some point something is not clear, just like feel free to write here too. Yeah, should we start? Should we wait a couple of minutes for like someone else or?
Sure, I think we can start maybe.
Sure. Okay, so today I'm talking about the part 9, 10. Oh wait, did we put recording? Yeah, okay, yeah, I think we have a recording. Okay, so we're talking about part 9, 10, 11 today. And so the emphasis today I'll try to do on the exercises because I think they are very important, especially because the topics are kind of like conceptually easy, but like you have to get like a good feel of them and how do you use them in set theory. So yeah, so let's start with a couple of things. So part 9. Um, so yeah, today we're gonna talk about axiom of choice first and infinite sets, of course, and we're gonna start with the theorem 9.1. That's kind of like summarizes what Nazir was doing last time, but also it's something new. So we have 3 statements. First statement is there exists an injective function f from z plus to a, where a is just like some kind of a set. And yeah, injective. And you have to remember that it doesn't have to be surjective. So a can be bigger than z plus, but because it's injective, we understand that uh, a should not be less than z plus. Okay, that'll give us something. Then we have the second statement. There exists a bijection of a with a proper subset of itself. Okay, bijection of a with its proper subset. If at some point my handwriting is awful, please let me know. I'll try to erase and rewrite it. And okay, a is infinite. Great. So, and now we have to understand that these 3 statements are actually equivalent. When we say statements are equivalent, it means that you can get a statement 2 from statement 1, but you also can get otherwise statement 1 from statement 2, and etc. So, how do we prove that statements are equivalent? Well, there are a couple of ways. You can, of course, prove it like this and like this, like this and like this, and because equivalency is how do you call it, transpositive, transformative, it basically means that if 1 is equivalent to 2, 2 equivalent to 3, that means 1 equivalent to 3 immediate after that. Okay, but we also can do it in a cycle. We can do from 1 to 2, from 2 to 3, and from 3 to 1. That's probably what we're gonna do today. Okay, yeah, so just let's start with a proof. Is that clear? Like the statement of the proof? By the way, when I share the screen, it's really hard for me to see the chat. So I would prefer if you guys can like speak up because I don't see the chat well.
Okay.
Oh, nice. Okay, so I'm erasing this. Okay. So to prove the first implication, what do we have to do? So basically, what we can try to see is that if f z plus is the image of z plus and we denote it by b, it would be a set of all images of z plus. And then what we're gonna do is we're gonna do the following. We're gonna say how about we do thing like we want to do like a recursive definition of something. So what we're gonna do is let fn be denoted by an, right? And so because f is injective, we know that an cannot be equal to am. Well, of course, if they're not equal. Okay, and so we want to define the following function. G from a to a minus a1. Okay, so what does this mean? Is that this function would be from all elements of a, but the images can be like all elements of a except for a1, right? Because it's a difference of two sets. Sure. And so what we have is that GAN is equal to AM plus, and GX is equals to X for X which are not in the set of B, right? Because we have to account for the thing that A may be bigger than D, and we have to define the G on all set of A. So this definition would work for the part of set B, and the definition works for all the rest of A, right? Okay, great. So what does this function, which is kind of weird, gives us? If you draw it schematically, like you have in textbook, basically here's your set B. It has numbered elements A1, A2, A3, blah, 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 blah. And they are the images of, 1, 2, 3, blah, 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 blah. And you have A minus B, and they are just kind of like returning to itself. So like if you had X, like fx would be equal to X, gx would be equal to X. And for this ones, the function shifts them by 1, like this. And we can do that because we know that B should be infinite, right? Okay, nice. And so, okay, what do we have now? We wanted from the statement that there exists an injective function from Z plus to A, get to the statement 2, which means that there is a bijection of A with its proper subset. Did we find a bijection in the end? Hello? Hey guys, can you see how do we do a bijection in here? If no, I can try to explain further.
I know what it is.
Nice. So basically, can you explain what subset of A did we biject with A?
Can you please go over it again? I'm sorry.
Sure, sure.
Can you precise what is A and B again, please?
Oh, yeah, sure. Okay. So basically, we know from statement 1 that there should be some injective function from Z plus to A, and A is just a given set. And B is the set of all images of Z plus, right? So, yeah, how can I erase part of it? Yeah. So basically, if we have, if we had set Z plus, and we have set A, which might be a bit bigger than Z plus, and we have all images, all those images would be set B. So we know that B is a subset of A. And we can have stuff in here which is not an image of Z plus. Okay? That makes sense?
Yeah. So B is the A is no the bijection you talked about. It's B.
Oh, nice. Yeah. So basically, we just made a bijection by defining the function G from A into B. Oh, no. Sorry. From A into A minus A1. Yeah. Let me explain why. Because basically what we're doing is we're taking a set A. Yep. We're taking a set A. And we're taking a set B, which is an image of Z plus. And we're taking all the rest that we don't really want. And we define a function G. The way we define a function G is that for all stuff in here, Gx is equals to X. So it doesn't do anything with those elements. They just like stay the same. But with elements in here, A1, A2, blah, 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 what we're doing is that GA1 is equals to A2, GAN equals to AN plus 1. So the function G shifts them by 1, right? So basically what happens is that we defined a function G, which is an injective function. And basically what happens is we just found a way to take A and send it with a function G to the set A minus A1. Why? Because all elements here stayed on their places, and all elements here were shifted by 1, right? So the only uncovered element by this function was this element, right? And we can shift it like here because it's an infinite function B, right? So does it make sense now?
Yeah.
Nice. So we just found a subset of A, which we could like map with A. So the statement B is done. Yeah. So now we want to prove that from statement 2, we can go to statement 3. To remind you how they sound, the statement 2 is there exists a bijection of A with a proper subset of itself, which we just proved, and we want to prove from it that A is infinite. Okay, nice. But actually this is easy. Why? Because if you remember, what we did before is in somewhere in like earlier parts of the chapter, we said that a finite set cannot have a bijection with its proper subset. Sorry for my handwriting. Okay, I think that was mentioned by Gaurav, right? And so basically what happens is that we know that finite sets cannot have bijections with its proper subsets. And from assumption 2, we know that set A has a bijection with its proper subsets. We also know that all sets which are not finite are infinite. So the only conclusion we can get from here is set A is infinite. Or basically you can just use a contrapositive of this fact, right? Does it make sense?
Yeah.
Great. Does it make sense for everybody else? Let me look at the chat quickly. Okay. Nice. So now what we want is we're only left with trying to prove that from statement 3 we can go to statement 1. So statement 3 says that A is infinite. We want to prove that there exists an injective function f from Z plus into A. And it kind of makes sense, right? Because if there was no injective function from Z plus to A, it kind of means that A is less than Z plus. And we have this feel that Z plus is like the smallest infinite set we have, which is not really true, but because you can have like, you can take a subset of Z plus, which would still be infinite, but in some sense it is. Okay, so we're trying to prove that. And then what we get is, a second, my
Hey,
notes.
Aiya, I'm sorry. Could you remind me what is the definition of infinite set?
The infinite sets are sets which are not finite.
Then what's the definition of finite set?
That was Gorov parts. I think it's a set that has a bijection with some subset of like 1, 2, blah 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 n, right?
Okay, thank you.
Okay. Okay, so now we want from the set, from this get to this. What we're doing is that first, because A is not empty, then we can choose a point A1 and say, hey, how about F1 would be A1? And then because like, you know, it's an infinite set, we can go like this and be like, F2 would be A2 and blah, 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 blah. And we can just like keep on doing this, right? And so yeah, basically what we do is we just keep on like defining defining function f like this, and if at some point we stop and we run out of elements of a, like say at point n we take a n and this is the last element and we have no elements of a, it means that a is a finite set. And so basically we have a contradiction, right? So we're kind of using an induction principle here. Does it make sense what we're doing? We're taking an like just any random element a1 out of the set a, and we're saying, okay, nice, so let this be f1. Then we're taking all other elements from here, so a minus a1. We're choosing any random one here, and we're saying let this be f2. And we keep on doing this by induction. Does it make sense? I think somebody wrote something in the chat. Oh, okay. Thanks, Gaurav. Yep. So, and just by doing this simple thing, if at one point we run out of elements, it means that the set A is finite. Otherwise, because A is infinite, we can just keep on doing this forever, and then by induction we have an injective function from z plus to A. Does it make sense? Hey guys, does it make sense?
Yeah.
Nice. Okay. So people say it makes sense. But now let's see if we can like try to formulate it more formally, right? How about we go and write it something like, we define a function f1 to be a1, where a1 is just some randomly chosen element. And then what we do is we say fy is equals to an arbitrary element of the set A minus set F 1 blah 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 I minus 1. So we're just taking the rest from the one that we didn't choose before. Okay, I because in 1. Okay, so that looks kind of like a recursive formula, something that Gora Fornadir taught us to do last time. But note that it's actually not acceptable. Why? Because before, a recursive function was like strictly defined. While here, what we're doing is we're arbitrarily choosing it. And so for example, like before, what I think Gaurav and Anjir did in their chapter, they did a following function. They did h1 to be like a smallest element of A, and then hi smallest element of the set a minus h1 to I minus 1, right? So each time they were capable of taking the smallest element. I think it was some point when a was like a subset of z plus or something, right? So in this case, you have a smallest element, so you can always just rigidly define what your h would be. But in our case, we cannot really do that because we're talking about some random set A, which can be any set, and we don't necessarily have a smallest element in there. And so we're here evolving into like having to choose an arbitrary element an infinite amount of time. And basically, people were doing it freely, and honestly, we're doing it freely in a lot of math classes. But at some point of time, what mathematicians noticed is that this thing is not always straightforward. So because what happened is that they found a bunch of like really weird outcomes of using an assumption that you can always take an arbitrary element infinite amount of times, right? So I think once in our math club we talked about those things, like say for example like the Banach-Tarski paradox. I don't know if you have ever heard of it, like the paradox when you like take one orange and you cut it into like smartly in some pieces and you got two oranges with the same volume from the same pieces, just rearranging them. Like of course it's kind of like a simplistic way of explaining it. They're doing it not with oranges but with specific sets. But yeah, basically like you get a lot of very weird outcomes by using this choice axiom, right? And so for some time in the math history, people were really confused because they didn't really want to accept all the results they got, like the Banach-Tarski paradox, right? And so they were doubting if the choice axiom is actually true. And so I think still a lot of people, like a lot of mathematicians, they like assume choice axiom in their list of axioms that they use for set theory, but there are still like mathematicians, like I met a couple who are working on a set theory and their list of axioms doesn't include like choice axiom. And yeah, and they're still doing some cool math. I think we even talked at one point about like infinite games and how you can like assume like a country, like the axiom of determinacy, and do all kind of stuff with it. So you don't have to assume it, but a lot of people do because choice axiom is a very convenient one, because it's really hard to work with something when you cannot make an arbitrary choice, because in a lot of ways we're working with sets that are very arbitrary and we don't always get to like choose how they're constructed, but we want some nice functions that work on them, right? And so we want those functions to work, and sometimes we need those functions to just take an arbitrary element because we're not really sure what kind of elements are in there, right? And so that's why we need that choice axiom. Okay. So basically, what happens is that in this chapter, we're going to talk about axiom of choice, that from now on, we're allowing ourselves to assume in our like proofs that follow after. Well, actually, we're secretly using them before, but like now we understand we're using them and we have to acknowledge it. Okay, so how to define it rigorously? So for example, okay, so for example, we want lemma 9.2, right? Existence of a choice function. Choice function. Oops. So let collection be like B be a collection of non-empty. This is important as they're non-empty sets, and they don't have to be disjoint. Don't have to be disjoint. Don't have to be disjoint. And so there exists a function C, because choice, from the collection of sets into the union of B. B is a set in the collection of B. So I know it kind of like a scary notation thing, but imagine you have like sets, like say B1, B2. Of course, it may not be a countable collection of sets, but like, yeah, you have some kind of sets, and we call this set of sets a collection of sets, fancy B. Kind of looks like a Russian B though. And basically what we're saying is that this is us choosing a set, and the image, notice it's not a set, it's an element of one of the sets. So it's a function that in which you input a set, but the image would be an element from kind of like a union of all this collection of sets, right? And this we call a choice function. But you have to be careful because we're not taking like any random element. We want this element that it inputs to be an element specifically of the set we have chosen. So like, say, if we're given a set B into our choice function, we want the CB to be an element of B, right? So basically, if we're plugging some set into this choice function, we want this choice function to give us an element of this set, not of this set, but of this set. Why? Because it's choice function. We just want it to choose one element from a set for us. Okay, and so that's what a choice function is, and we just want to say that it exists. Oh, okay. Yeah. So you would ask me why this is a lemma, because we already assumed axiom of choice. The difference between this lemma and the axiom of choice is that, as we specified before, the sets doesn't have to be disjoint, while in our axiom of choice, what we did is we wanted a function that works like fy equals to like a minus f1 blah 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 yi. So it kind of excludes all other possible elements, right? So we know that it would be disjoint, but in here actually we can have like sets which have a lot of common elements, right? So we have to make a specific lemma for this. Okay, I'm gonna stop and ask, is everything that I told so far understandable? Do I have to re-explain anything again?
No.
Okay, great. So what we're doing in here is actually a super smart move. I was trying to first prove the lemma by myself without looking at the proof, and I gave up. But yeah, so let us define B apostrophe to be a pair B and X. Oh, sorry, a set of pairs where X is in the B. I can hear Nadir laughing at me. Okay, so basically, like, say for example, if your set B is 1, 2, 3, what you're doing is B1 would be a set B1, B2, B3, right? Okay, so we're making a new set out of this. And so what happens is that B apostrophe is now a collection of like ordered pairs, right? Because we can just like wait, give me a second. How do we order them? I forgot how do we order them. If you have, wait, I don't think it's an ordered pair. So okay, forget me saying that it's an ordered pair. It's just a collection of pairs. Okay, and so basically the set B would be a subset of a Cartesian product that looks like collection of sets B with union of B. Okay, so what this Cartesian product means is that you're taking all possible sets which are in the collection of B, and you're taking all elements of all of those sets, and you're taking all possible pairings of them together. That's a Cartesian product, right? And so we know for sure that this is, of course, a subset of this. Nice. Once we know that, once we know that, we also know that B apostrophe is, of course, non-empty. Great. Now if B1 and B2 are different, so they are not equal. By the way, notice that they still can have common elements. They're just not totally equal. We know that B1 apostrophe is not equal to B2 apostrophe. Is this statement something that you guys understand? Because otherwise I can try to show you why this is true. Do you understand why from this we have that this follows?
It means that if B1 and B2 are disjoint, then B1 apostrophe and B2 apostrophe are disjoint. Yeah.
Actually no. B1 and B2 can have common elements. They don't have to be disjoint. They just have to be not equal. So like say yeah, so like if B1 can be like 1, 2, and B2 can be like 1, 2, 3, like they still have common elements, but they are not totally equal.
Yeah.
So do you see now why B1 apostrophe would not be equal to B2 apostrophe?
Yeah, that makes sense.
Great. Well, you can just simply show it because they have to have at least one different element, say 3. And so this set would have a lot of pairs with 3 in it, while this one wouldn't have them because it doesn't. Oh, sorry, no. This one would have pairs with 3. This one wouldn't have pairs with 3 because it just doesn't have 3 in it. So this set would have elements which are different from this set.
Okay.
In the chat. Oh yeah, thank you. I forgot you can call it B prime. That's much easier. Okay, so and now what we're doing is is that we realize that they're not equal. Can we realize that they are disjoint actually?
I think yes.
Nice. Why?
Because if B1 and B2 are disjoint, then all the couples would have different numbers or elements of B1 and B2, so there won't be any couple with the same elements.
Oh, nice. Okay, so basically, to say it more officially, imagine that they are not disjoint and they have at least one common element, say CX is their common element. But then this C, for this element, because it's in the B1 prime, it should be B1X. And because CX is in B2 prime, let me erase everything. Because CX is in B1 prime and CX is in B2 prime, we have that C has to be B1, and here C has to be B2, and then we get that B1 is equals to B2, which is a contradiction. Nice. So we realize that they cannot have any common elements, so they are disjoint. Can anybody guess what we're going to do next? Okay. So if people have a bit of a hard time trying to figure out what we're doing next, let me recap what we have done before. First, we assume axiom of choice, which would be shortened as AC. An axiom of choice tells us we can choose elements from disjoint set. We want to prove lemma 9.2, which basically tells us can choose elements from not necessarily disjoint sets. What we did is from sets B1 and B2, which can have common elements, we constructed B1 prime and B2 prime, which are always necessarily disjoint. The function would be a subset of the Cartesian product. Yep, and we know that this B prime is always a subset of the Cartesian product. Okay, so does anybody know what we're gonna do next? We know this, we want to go to here. The only difference between them is that this one wants you to have disjoint sets, this one doesn't care about disjoint sets. We have sets which can have common elements. We constructed smartly sets which are kind of like going from those sets, but which are always disjoint. Yay, Nadir is right. By the way, Nadir, feel free to speak up because it's really hard for me to check the chat when I'm sharing the screen. Okay, so Nadir is telling us now we have disjoint sets, why not to use axiom of choice, and I like his idea. So basically we have we have some kind of axiom of choice. We can use it for sets that look like this, right? What we're going to do is by the choice axiom, there's a set C. Okay. Give me a second. To say what Nadir told us formally is we're gonna make fancy C, which would be a collection of those B primes. Oops. Right? So we're just taking all the B1 prime, B2 prime, and etc. Right? We're taking a collection of it, and we know that those B primes are always subsets of our Cartesian product, which looks like this. Nice. So by axiom of choice, there exists a set which consists exactly of one element from each of those subsets, right? Okay. And therefore, for each B, this subset, which would look like, say, so like B prime X is an element of B prime, right? So our choice function would give us this. And every time for each of the different sets, the first coordinate of this pair would always be different, right? And so, can you guess what we're gonna do next? So, just to remind, this C is a choice function that we know exists because of axiom of choice. We applied it to this collection of disjoint sets, and for each of those disjoint sets, we get an element of the set which looks like this. And now, what are we gonna do? Right here. So, can somebody remind me what we wanted to prove?
If A is in 3 to 1.
You need to get like the C function should give you an element of the set B which you input inside.
Nice. So we wanted to have a choice function that from a set B would give us some element A which is a set B. The only difference for lemma is that those sets that we have in here may not be disjoint, right? That we wanted to prove that we can do this. What we reached so far is that we have a choice function, little c, that from each b prime gives us an ordered pair. Oh, sorry. Yeah, I messed up this part. Oops. This should be like B. Yeah, B. And this doesn't have prime, right? Yeah. Because those are the elements of the B prime, right? So from each set B prime, we get an element of B prime. For set D prime, we get an element of D prime. Nice. And if you notice, X is an element of B, Y is an element of D. So, and because each time we get like different sets, we have D prime, D prime, and stuff. What can we do? Yeah, Nazir said, we're done. Why? Because you basically just take the second coordinate all the time. And so if you just keep choosing second coordinate from this pair, then for then basically for the set CB, you get X, and X is an element of B, right? For CD, you get Y, second coordinate of here. And we know that Y should be an element of D by definition. So we found a choice function that we wanted, and B and D are not necessarily like different like necessarily disjoint, right? So we're done. Was it understandable? Like, did you guys get the proof?
Yeah, I think it's good.
Okay, so basically, just to recap, like if you didn't get the entire proof like immediately, it's fine because the proof wasn't like that easy. But what you have to realize is we did like a very, very smart trick. We had a collection of sets like say A, B, C, D, blah, 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 and they're not necessarily disjoint. But what we did is we made a like a new collection of sets like B prime, which was just like a set of like ordered pairs, like BX, BY, and stuff, right? And now like those sets, they have to be disjoint. So like from like sets that were not disjoint, we smartly constructed disjoint sets, and that was like the beauty of the proof. is because we were able to like find disjoint sets out of not disjoint sets and use the choice function. And like set theory has a lot of smart tricks like that, and you have to get used to them. Eventually you'll get used to them. Okay, so what we have now. Okay, so just to make sure, AC talks about like infinite sets, right? When you have an infinite collection of sets, then you can go and choose an element out of those sets. But when you have a finite number of sets, like say 4, you can always choose an arbitrary element of it, and it's fine. Like basically, basically that's like the difference, because you don't have to have axiom of choice to have the fact that you can just arbitrarily choose an element out of like finite number of sets. You only need axiom of choice when it comes to infinite number of sets, and that's like the big difference, right? Okay. This trunk form applies to the arbitrary collection of. Okay, yeah, sure. And sometimes people call this thing a stronger version of like axiom of choice, but I think most of people just call it axiom of choice. So yeah, but feel free to use any notation you like. So now we'll try to do a couple of exercises, and we'll try to do maybe like 4 or 5. And I know it may be a lot, but also, well, we have time. And I think it's better if like even if we don't finish all the chapter today, but you'll get like a good grounded idea of what we were talking about today. So exercise 1, also feel free to open your books because my handwriting is bad. Define an injective map G from Z plus into XU, where X is a 2-element set, without using the choice axiom. Okay, so does everybody knows what that is?
I was just going to ask why we have the omega with the x.
Why you have to what?
Like it's x omega in the textbook, but xu in your textbook. Anyway, why do we use it?
Wait, why do we? Sorry, I don't hear you well. Why do we use what? Oh,
I think Professor Shu wrote it in the chat.
by the way, while Theodore is writing, does anybody have ideas for the problem? Oh, why do we use the omega in this? What I believe, like the way I was solving this thing is it's like kind of like all kind of combinations of like 0, 1, 0, blah 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 blah. So it's like basically you can think about it as a binary number. I think it like this was defined in the chapter. Gaurav, Nadir, do you remember like how this was defined? Because I think this just means all kind of like say binary numbers, like this one. maybe like stuff like that. It doesn't have to be infinite, by the way. Oh, nice. Najir says it's in section 5. Najir, can you read like a definition of it? Because I think I'm right, but like just to make sure. Or do I have it here? Okay, so I think Professor Shu is writing that it's like a Cartesian product, right? Okay, great. So it's actually the same. Let me rewrite it. So we know that x omega is a Cartesian product like x1, x2, x3, blah, blah, blah. And those xi's are just elements of x, right? So in our case, when x is equals to 0, 1, x omega is basically like, oh wait, sorry, that's is a collection of like W tuples for which you have like say 0, 1, 0, blah, 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 and all kind of W tuples like this. And W can be infinite. Or also actually can be finite. Like say x2 would have only 0, 0, 0, 1, 1, 0, 1, 1. Okay, does it make sense now, Theodora?
Yeah, I think you have this kind of thing. You have this kind of definition. Say that okay, a to the power b, where a and b are both set, just means you collect all kinds of map from a to b. Maybe another way, where from b to a. I'm sorry.
Oh wait, I think the definition given in 5 by Cartesian product is that you're just taking like a Cartesian W tuple and you take a collection of it, like of all kind of.
But what if your omega equals to r, all the real number? Then you cannot really write it like this, right? Which is why maybe sometimes you have to write it as a map. All this kind of tuple can be seen as a map, right? And the map such that this map, you gave me any number in R, any real number, I gave you either 1 or 0. Okay, so that you can treat this kind of tuple just like some kind of function or some kind of map.
Oh, I see what you mean.
Yeah, so you can see the definition on page 37. I don't know whether you got the same version of my textbook or not. On the definition, well, what is an M tuple of element of X? It's just a map from 1, 2, 3 until M to X, right? So this is for the M tuple. But now, if it is not omega tuple, if it is not some finite number tuple, if it is a real number tuple, like R tuple, R is a real number set, then it has to be still a map, right? But now the domain is all the real number.
Okay,
so this
okay.
can also seen as an infinite Cartesian product.
Okay, makes sense.
Mm-hmm.
So it's a function between R and I'm trying to see like the rigorous definition to write it on the board. You said page 37? Because I don't see
Maybe
did
the
you
last
include a definition?
Yeah, maybe.
Oh yeah, I see the page 38 where they say, so basically they say that that xm is denoted by Cartesian product of a1 product am, so like m tuples of x. Okay.
Yeah.
Just
the right as an example. For instance, if you have this, x to the r, x to the power r, of course you cannot really imagine. Okay, you may have a lot of multiplication of this x, right? But then now it's not countable. Then this consists all this kind of, you can see all this kind of function, which is a set of functions, such that this functions is a function from r to x. Okay.
Alternative definition
Yeah.
set of functions. Okay, set of functions from where to where?
From the power to your base.
Oh, so it's like from W to X?
Yes, from W to X. So if you define it this way, then you can actually have your W to be not only some finite number like m or like 1 or like 2 or like 3, right? 3 tuple or maybe 4 tuple, but it can also be all the nature numbers or even all the real numbers.
Oh, okay, I see. But do you mind if we use like the book definition for this exercise? Because if we use your definition, the exercise 1 is not an exercise anymore. It just follows from definition then.
Yeah, of course. Yeah, I just want to to remind you because later I think when you prove this Tikhonov series, I think chapter 5, you will use this kind of notation to understand what is the infinite multiplication or infinite Cartesian product. Okay.
Okay, so coming back to exercise 1, does anybody have ideas of how do you find an injective map J from Z plus into XW? Like any ideas, just like anything that comes into your head. So oh, sure. Tell us your idea. Wait, what do you mean by the n tuple? You mean like the n's position in the tuple is 1? Oh yeah, that works perfectly. So basically what Nadir is saying, if you got F1, you have it should be 1 0 0 0 blah, blah. And so if you have 2, then you want it to be 0 1 0 0 0 0 blah blah blah, and so forth. So I think it works perfectly, and it's an injective function. Can you prove it's an injective function? That's like super easy. You can do that. Oh, Osman can prove it. Can you prove it's an injective function for us?
Yeah, I think I can.
Okay, so
Exactly
Najir,
what yeah.
yes, Najir wrote in the chat. So basically, if n is not equal to m, it means that you will have 1 on the nth position, and
Or
you'll
we
have
can say
position.
that if the tuples are equal, then all the elements in the tuples are equal, then n and m would be equal.
Oh, nice. That's even better. That was more formal. Nice. So first exercise is done, and so the aim of this exercise, I think, was basically to show that if you like, you don't always have to use choice axioms. Sometimes you can directly build a function out of something, like, and it kind of makes your proofs like less demanding for like axioms. That's good because more people can use them. Okay, so the second exercise, find if possible a choice function for each of the following collections without using the choice axiom. So 2A, the collection A of non-empty subsets of D plus. Okay, A is a collection of non-empty subsets of Z plus. So basically, you're given some subsets of Z plus, and you have to choose an element for each of them. Note that those subsets can be infinite. Gaurav, any ideas for choice function? It's difficult, like. Huye, any ideas for choice function? Oh, yeah, I think Storm killed Gaurav's connection. Oh, Nazir is saying we can use the well-ordering property. Well, not actually, because well-ordering is a part 10, and we didn't get into that. Okay, well, actually, remember when I was telling you about a recursive function that we did in the previous chapter that is a well-defined function?
I wasn't here.
Okay, so I was reminding you of a function that looks like h1 smallest element of A, h2 smallest element of whatever is left in there and stuff, right? So using kind of like a similar idea, how can we define a choice function on a collection of subsets of Z plus? Notice a Z, it's not Z, it's a Z plus, right? So, oops, ah. Okay, so the Nazir said that what he meant by well ordering is taking the smallest element of all possible sets, right? So whatever like say you have some kind of like subset B of Z plus, and this B is in the subset, and B is in the collection of A, then because B consists only of positive integers, you can always find the smallest element from B. So basically you're saying CB equals smallest element of B, right? And notice that your choice function doesn't have to be injective. So even if those subsets of Z plus have common elements, and those common elements happen to be also the smallest elements, it's still fine. Okay, so we came up with the choice function. Nice. How about I'll give you a try on the second B. So the collection B of non-empty subsets of Z. Oh, that's trickier. But now that you know the idea for the 2A, can you guess the idea for 2B? Okay. Any ideas, guys? So how usually subsets of Z look like? Well, say if you have like -5, -4, -3, -2, -1, 0, 1, 2, you have a subset of Z. So how would you try to choose an element out of all of this so that your algorithm for choosing an element would work for basically any element? Well, I'll give you a hint. What I'll really prefer to choose is 0. Because if you think about it, choosing a largest element here may not always be possible, because I can have subsets which are like 0, 1, 2, 3, 4, blah, 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 and they're infinite, so I don't have a largest element. But also choosing like the lowest element is also not always possible, because you can have like sets that go to -infinity, right? So choosing 0 or something like 0 can help you, because it's kind of always in the middle, and you always have that middle in any of your subset of Z. So any ideas for what choice function we can choose? I'll just start naming random people. Takan, any ideas for a choice function?
Sorry, I'm still thinking that.
Okay. So can we do something like the smallest element of Z? But we don't always have the smallest element, but something that's like the smallest element of Z. Or better, can we make a Z plus out of Z and then choose the smallest element? Is there anything that can help us making Z into Z plus? Come on, guys. Well, not Z plus.
Yeah.
Z plus. Yep.
Function.
Sorry, I didn't hear. What did you say?
A function can make v to
Yeah.
x.
What kind of function? You all know that function. You know it from like primary school, maybe middle school.
Cubic function.
Cubic function? Well, if you have like -3 into,
I want to say square. Square.
well, sure, yeah, square can help you. So like basically what Osman is saying is, let us take any integer, take it in a square, and then we can choose the smallest element, and that actually works pretty well.
Yeah,
Well,
that would be 0.
you can do even easier. You can just take an absolute value.
Yeah.
It also helps you, right? So basically, how about we take an element with the smallest absolute value, and then always would be an element in here. And for any subset of z, we can always find that smallest element with absolute value, right? Because it's usually either 0 or 1 or 2 or whatever, or -1 or minus. Nice. So we have a choice function for a collection of subset of z. We notice that it's really hard to choose a smallest element when you have stuff from -x to x, right? But if you order it in a different way, if you order it like 0, 1, -1, 2, -2, you immediately have smallest elements from this side, right? But sometimes it's about like ordering stuff smartly, so you can find the leftmost element, right? That's the important idea of the exercise. Okay.
Can I just ask a question about this one?
Sure,
So
sure.
like, when you use the absolute value, like if you don't have 0 in this set, don't you get like two numbers which you pick? Because like the smallest absolute value, for an example, if it's 3, then you get 3 and -3, and you actually pick two
Oh,
elements.
yeah. Nice. Thanks so much, Theodora. That's a super helpful suggestion. What I forgot to tell you is you can have like a more complicated algorithm. Say, for example, first you choose the number with the smallest absolute value. Like you get, for example, that the smallest absolute value is -3 or 3. And then from this, you can choose, for example, the positive one. And then you always get like the one number. But yeah, thank you. That was a super good thing to notice. Okay, does everybody get the algorithm now? So
Yeah.
yeah, nice. So first we choose the number with least absolute value, and if you get two numbers, you just choose a positive one. Nice. Thanks a lot. Okay, so to C, the collection C of an empty subset of the rational numbers Q. Subsets of Q. Okay. We have to come up with an algorithm in here. Any ideas?
We have to do the same thing, or
Yeah, just maybe like twice, right?
okay.
Can you explain in more details how do we do the same thing?
No, I was asking. I'm lost.
Oh, yeah. So you're basically we're trying to find a choice function from subsets of the rational number. So say, for example, you have a subset of Q, which is like -2/3, 1/5, 7/8, and you're trying to choose an element out of here. And you have a lot of subsets like this, and you're trying to choose an element out of each of them. Okay, any ideas? Well, guys, how do you prove that you have countable number of rational numbers? Does anybody remember? I'm sure at least Nadir knows, because Nadir did a bit of an... Oh, Huye and Zikan also knows, because you did analysis. So how do you prove that Q is countable? Huye, how do you prove Q is countable? Or how do you like order Q?
I'm currently checking my notes.
Okay. Or it doesn't, we don't have it to be naked this way. Well, guys, just choose any algorithm for... Okay,
I remember that we started from 0 and made them 1 by 1.
you starting from 0 and you do what?
And made them 1 by 1, like from 0, then 1, and -1 to -2. So
Yeah, that's for
I can
integers.
remember.
How do you do the same thing but for rational numbers? Well, say you can take this to be denominator, this to be, I forgot how you call this part of the rational numbers. Like this would be this would be this. And you do like 0 minus 1, 1 minus 2 minus 2, and you do minus 1, 1, 2, 2. And so the points on this grid would be like all possible, thank you, numerator and denominator will be all possible rational numbers, and you can just go like, woo! And that's give you a good order of them, right? And that's actually how you prove that they are countable. You write them in a grid like that. Notice that we have all positive and all negative denominator and denominator, and you just like go like a snake, and you know that you will always cover all of them. Actually, sometimes you would cover some number twice, but it doesn't matter because you can just like erase them out of your line. Because for example, you have 1 when you take 1 divided by 1, but it's also like 2 divided by 2 and stuff, but it doesn't matter. What matters is that you found a way of like ordering them well. And so once you order them, you can just take the leftmost number, right? Say, yeah. So like, say you have 1 divided by -1, and you have, I don't know, like 2 divided by -1, and you have some number like, I don't know, -2 and like 5 or whatever. And you see that this one comes the last, this one comes second, and this one comes first. So you take this one as your number, and this is an algorithm, so it doesn't require you to have an axiom of choice because you order them yourself, right? So does this make sense? And you don't have to order it this way. You can order it any way your fantasy would allow you to. Oh yeah, I was thinking of P plus Q. Yeah, so basically what you can also do is you can say if your number looks like P and Q, then you can just take like say P plus Q and choose like the smallest the smallest possible like sum of P plus Q, maybe like an absolute one, right? And then if you get like say 1 divided by 3 and 2 divided by 2, you can just like say the one that was like the smaller p, and then it was positive p if you get like 2 of them. Well, so like you can come up with all kind of like algorithms for that, right? Or you can even do maybe some kind of like an dictionary order, right? You can, for example, first choose a rational number with the smallest absolute value of q, and then from all of them which have like the same q, you choose the one with the smallest p, and then from them you choose the positive one. So like you have like guys, like this is why math is like beautiful. You have so many options. You can always do it in like your own way, right? So yeah, just you can sit sometime and be like, what are all possible way I can like come up with like fancy ways of ordering stuff or choosing stuff, right? Okay. 2D. Well, actually, I'll still use this one because it's kind of tricky. You have a collection D of non-empty subsets of xw, where x is 0 and 1, and they ask you for the choice function, and there is no choice function. Why? Because, well, so basically, if your w is like infinite, what happens is that you can find a bijection between this and real numbers just by using their binary form. So you know that like, I don't know, pi can be written as like, I don't remember, but I think it's like one blah blah one dot something 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 something, and like you can definitely see how that can be written as like, I don't know, one one blah 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 blah, blah. And so, and we know that there is no specific choice function that we know it exists for real numbers. Yeah, so basically we know that it exists, but we don't know what is that function that helps us to choose from real numbers. So sometimes in math, when you prove theorems, for some sets you can find a choice function easily, like we did for ABC. For real numbers, there is no way people found so far to try to make a choice function for the subset of real numbers, but we know it exists. Okay, so it's 6:30 for me. I think it's like 8:30 in China. Do you guys want to have a break because we're working for an hour and a half so far, or you want to have a break later? I don't really care.
Maybe we can have like 10 break now.
Okay, nice. So how about we come in like 10 minutes? Hey, can people tell me if they're here and stuff? Because I think
Yeah.
it was 10 minutes.
Hello.
Uh, hey, Tikan, Huya, are you here? Nice. Nadir? Okay. I think Nadir, Huya, are you here? Okay, maybe we should wait for a couple more minutes. Oh, I see Nadir. Is Gore still experiencing storm? Oh my gosh. It should be severe. By the way, Nadir, is that going to come at some point to the seminars or whatever? You should get him in. Oh yeah, maybe that's because it's too early for him, like the time doesn't match. Oh my gosh, Zach is changing his major to computer science? No, you should tell him not to do that. No, I can't believe Zach is betraying us. That's so sad. We should get him back. Show him how beautiful math is. Okay. I think we kind of should start. Well, and I think that Huya can, like, if she would miss something, she can always go back to the recording. Because it's been like 15 minutes, I think. Okay, and I think most of the people are here. So the exercise 3 is saying that we have a set A, and we also have indexed family of injective functions. So we have a lot of functions which are also indexed conveniently with positive integers, which is good. And they are injective. And we know that Fn has a domain from 1 to n, and its image lies somewhere in A. First, we want to show that A is infinite. How can we possibly do that? Well, you have to imagine that the functions are injective and n can be any. So what happens is if A is finite? So imagine, so prove, suppose A is finite. So imagine it has m elements in total. What would happen with this family of functions, which have to be injective and which domain has to be like also like numbers from 1 to n? Yay! Okay, great. So Nadir is saying take a function f m plus 1. It has m plus 1 elements in its domain, right? M plus 1. And it has to be injective. So it means no two elements can go have one image. And we have m elements in A, right? And so there would be one element which is left without a pair, right? And so, or it would have, but because f has to be defined on all the domain, it would just have to like, cross with one of the elements, right? So it cannot be an injective function. Well, you can say like more kind of like officially using like say Dirichlet principle or pigeonhole principle. If you don't know what a pigeonhole principle, please tell me, because I think you're gonna hear the word a couple more times. Well, feels like people know. Oh no. Okay, so pigeonhole principle basically tells you if you have some number of say rabbits, that's how I think Russians always explain it with rabbits, and you have n or m number of cages for rabbits. If you're trying to put all n rabbits in m cages, if n is bigger than m, then basically what happens is you would always have at least 2 rabbits in one cage. Right. Actually, it's a bit stronger. Usually you write as you take the whole number of this plus 1. So you will have a cage with at least this number of rabbits. And so basically we can just use it here because we have m number of m plus 1 number of elements. We have m elements, so it's like m plus 1 rabbits. Each rabbit has to be mapped to its cage, right? So, and like we cannot just like leave a rabbit like nowhere. So we would have a cage or an image which has 2 rabbits in it. So basically we would have an image which has 2 pre-images, and this means that the function is not injective, so a contradiction.
Yeah.
Nice. So we did exercise first half of exercise 3. Then they ask, can you define an injective function? So f injective from z plus into an a without using the choice axiom. And let me remind you that we always have an available family of functions that are injective, and fn is from 1 to n to a. Well, what we want is we just want to have like f1 equals to whatever set element of a, f2 equals whatever element of a and stuff, right? We want it to be injective. So, any ideas?
So you said that the family of functions fn is always injective from 1 to n to a, right?
Mm-hmm.
Okay.
Give me a second. I need. What's that one? Hey guys, any ideas? Hello? Hey guys, can you say if I'm audible? Because I don't know if you hear me or not. Oh, nice.
hear you.
Okay. Sorry. I realized my solution was a bit wrong. I had to go and check it out. But I think now I changed it a bit. Okay. So just any random thoughts that you got?
I don't understand the part when you say that we don't have to use the axiom of choice.
Oh yeah, so you're trying to build your own choice function without using axiom of choice. So basically it's like axiom of choice tell you there always exists a choice function for your collection of sets, right? But here they ask you don't use axiom of choice because you have to come up with a choice function yourself. And so basically they give you like as a supplement this family of functions, and you just have to build kind of like a general function from integers into set A. Okay, so how about we try to make one? So my first attempt when I was trying to solve the problem was say, how about we choose f1 to be f11, right? Because we know that a function f1 has only it goes only from 1 to a. Say it goes to a0, right? So this, why not? So then F2, how about you take F22 and you take, and then you take Fn to be Fnn. So what is a possible problem with a solution? Yay, okay, so this may not be an injection, so my first solution is actually wrong, but I think it gives you like a nice starting point to start from something, like that you get the ideas that you can somehow use the function that we already have to like, and the values that we already have for them. But like, okay, so how about we use, like, we make this one stay. How to make this one always different from the previous? Well, you can always say, well, how about we look at all possible values of, we have f21 and f22. We have two values in here, and we have only one value used here. At least one of them should be different from this one, right? And so we'll just say, and if both of them are different, we'll just take the smallest. So we'll choose all images which aren't equal to A0, and we'll take the smallest from them. Does it make sense? Hey guys, dear Osman, any comments on that? Does it make sense? Do you want me to give an example maybe of functions? How would that look like? Okay, Nadir says it makes sense. I hope it makes sense for everybody else. Nice. And so that's basically how you build a function. You can do it inductively, right? Because how do you show that? Say for example you have fn plus 1, right? You know that before you already had values f1 blah 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 fn. So you have only had n values so far. And you can choose your function fn plus 1, and you know that its domain has n plus 1 values. So at least one value would be free and was not chosen before. And if more than one value was not chosen before, we'll take all those things for i's which are not equal to any of the ones before. So like j is equals an n, I is equals an n plus 1, right? So we're taking all those images, right? And then we take the smallest from them. I don't know, infimum from this set, right? And that's how you define it. And so it would be injective because we specifically define it to not to repeat. And also we always have a value to choose from. Okay, so that was exercise 4. I kind of feel like we can leave the other 4 exercises because they get harder and harder. But like, how about you like read them, and if you have any problems and you can like discuss them, you can always write in our WeChat group and just like, you know, talk about them, solve them together. I can come with like solutions next time when we'll have like a spare minute or whatever. And for now we can continue with like the tense part. So tense part, well ordered sets, what Nadir mentioned before. Ordered sets. So basically, what's so nice about Z plus, and then what we used before a couple of times is that if you take any subset of Z plus, it always has a smaller element. Always has smaller element. And that makes our choice function so nice because you can just always choose a smaller element. Okay, and so basically, wouldn't it be nice to know that there exist sets like Z plus, which also have smaller elements? Well, I think it would be kind of nice. So let's talk about them. Definition. Set A was an order relation with an order relation is said to be well ordered if every non-empty subset of A has smallest element. So a couple of things you have to notice is non-empty subset and every. So basically, if a set A has some number of subset which have smaller elements, this is of course nice, but not all of its subsets can have smaller elements, right? And that's what stuck us sometimes because we don't always get to choose what subsets we would get. And also you have to note that we're specifically saying order relation. Why? Because, say, for example, is Z a well-ordered set? It really depends. If you're trying to order Z by a usual order relation, so when you're saying that, -3 less than -2, -1, blah, 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 it's not a well-ordered set. Why? Well, because you can always have something less and less in here, right? I can take a subset of it where it would be like 0, -2, -4, blah, 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 and it would never have a smaller subset, or a smaller element. Right, so I found at least one subset of Z which doesn't have a smaller element, but if I choose, for example, Z, and I'll define like a specific order myself, I'll call it order Aiya, the order that Aiya came out with. It may be a quite ugly order, but it doesn't matter. If I come up with some kind of like ordering, say 0, -1, 1, -2, 2, blah, blah, blah. So I order them in this way. So I'll say that. Oops, sorry. -1, 1, -2, 2, and stuff, right? So it's a new order. And using this order, any of my subsets always would have a smaller element. Like sometimes it would be 0, sometimes it would be -1, and etc. Right? So in this case, Z is well ordered with a specific ordering, right? So usually, what we're interested is there at least one ordering for a specific set so that it becomes well ordered, right? Because with not all the orders it can be well ordered, but if there are at least some, well, it gives us hope that we can work with it nicely. And so we have like a couple of examples from like say for example 1 is a dictionary ordering. I don't know if we mentioned what dictionary ordering is before, but if we didn't, let me just show. So say this is a Cartesian product, right? So it would have oh, okay, Nazir said that we did, but basically what you have is you have Cartesian products, and you can just like order them. So basically, like say whatever has 2 in its first coordinate would always be bigger than whatever has 1 in its first coordinate. Doesn't matter what the second coordinate is. And then if you have like 1 and 1 here, then whatever has like the biggest element is like bigger. So that will be like a dictionary order, because you're firstly ordering by the first term and only then by second term, like in dictionaries, you know, like you first order by first letter, then by second letter, and then by third letter and stuff. Okay. Then example 2 is you basically can do something like that with z plus z. Well, you kind of see why. Because you can first order by first coordinate anyway, because it has a smaller one and bigger one and stuff, and you can order them by second coordinate. So that's how it works. Okay, and example 3 I already talked about. So there are several ways of constructing well-ordered set. Okay, if A is a well-ordered set, then any subset of A is well-ordered in the restricted order relation. What does that mean? So basically, that's kind of understandable. What it says is, if A is some well-ordered set, then any part of it, like say a smaller subset of it, would also be well ordered if you're using the same order relation. So if you're using this one here, then you should use this one here too, and then you can claim it's also well ordered. If you're using a different relation, then it may not be well ordered. Okay, that I think is fine, and you probably get that. Okay, second, if A and B are a well ordered set, then so A is well ordered, B is well ordered, then a Cartesian product is also well ordered. Can you guess how can we well order it? Hello. Oh. Yay, Nadir said dictionary. Nice, yes. You just basically, you first choose the smallest element from like a subset of A, then the smallest from B, so you get the smallest element from the Cartesian product if you get the dictionary order. Nice. And so, as you can see, what happens is that if you have a finite number of things like this, so that plus, if you have like a finite number of Cartesian products, then you can always just order them by dictionary order, right? Or even if you have like, say, some well-ordered subsets, well, A2, A3, blah, blah. If you have their finite number of their Cartesian products, it's still well-ordered. And we just showed why. Okay. Well, it doesn't really work for an infinite number of the multiplication. Like, I mean, in the sense of like, of course you have a choice function because that's what your axiom of choice tells you, but it's not like we know really well how to order them. Okay. Okay, so given a set A, it would be a good question. How can we well order it? If A is finite, then probably a function from A into 1 blah 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 n can be used to order it somehow, right? Because basically, if you have element A, which is mapped into like say 3, and element B, which is mapped into like 5, because 5 is bigger than 3, you can just order so that B will be bigger than A, right? And so, like, if you have like a finite set, a function like that can help you to order it, right? Okay, and so basically any order relation on a finite set can be just made in this way, right? I hope it makes sense. So with finite set is always pretty nice. And then we have a theorem 10.1, which says that every non-empty finite ordered set has the order type of a section 1 n of z plus. So it is well ordered. Okay, so what does it mean? So order type is basically you're saying that if you have two sets and you can find a function f between them so that the following holds: if a is less than b, if fa less than f of b. So a function that preserves the ordering, and if you can find such a bijective function f, then basically two sets have the same order type. And well, I think it's a kind of an intuitive concept. You're basically looking at all groups that have the same kind of like similar order structure. Does it make sense? Yeah, okay, it makes sense. Said Nadir. Okay, so oh yeah, and the second implication of the theorem, basically what it tells us, because every finite set has an order type of some set which looks like 1, 2, 3, 4, blah 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 n. And because this is well ordered, well, because you can just order it like you usually order integers, then because this is well ordered, you can well order this. So any finite set is well ordered. Nice. Okay. Well, how do you rigorously prove this theorem? Okay. So first, every finite ordered set A has like a largest element, right? So we can actually just like, yeah, we can actually just like do this. Like we can always find smaller elements or larger elements. We can just order them by smaller or larger elements. Or we can also try to build a function that would look like this. So say you're doing f1 largest element of A, then f2 would be largest element of A minus f1 and stuff. I think I saw a message in the chat. Oh, how do I? No way. Oh, the section. Yeah, so basically we know that they have the same order type as the integers, and yeah, so basically Nigeria is right. So what I'm showing here is like one of the things. What Nigeria said is we can say we can find a function that maps our like say integers into the like A or otherwise, and then because we have a well ordering here, we just say that f1 is less than f2 is less than f3 and etc., and that would be our ordering. So that's what Nadir says, I think, and that's basically it. And we can just use again like the usual kind of thing when you say f1 is equals to like largest element, f2 equals to largest from rest, f3 is like largest from the other rest and stuff, right? So here would be the ordering, for example, right? It would actually be different, or you can do the smallest, but it doesn't matter. What we're doing is we defined some kind of choice function, and we used the orderings of integers to order the images. That's what important. Okay, so this was for finite, and so we see that finite sets are good in all kind of things. We always have choice axiom working there. We always have well orderings working there. Such nice sets. Well, sadly, not all sets are finite. And then what we have is that we have a lot of possible order types when it comes to infinite sets. So for example, we have z plus is one of them, right? Because you can find like a bijection of like different sets into this one. But if you notice, this one is a different order type. And then this one is also a different order type from both of them. So you have a lot of different order types. For example, you can have like z plus w, right? Okay, so you can show that you cannot have a bijective map that preserves the order for those sets, and we'll actually do that in some of the exercises. But yeah, for now, just believe me that those are very different order types. So you get into a very confused area once you step into like infinite sets. Okay, so, but it's still fine, at least now, when we have z plus w and w is like a finite number, because we can still use a dictionary order. What happens is that we also notice that dictionary order works for like when you have like countable number of elements, right? But once you step into like uncountable elements, we are very confused what can be like a well ordering for uncountable elements. So for example, z plus in like w, where w is not a finite number, this would be an uncountable set. I hope that Quora for Niger were shown it last time, I don't remember now. But like basically because it's uncountable, we don't really know how to well order it, right? Because we cannot use dictionary order anymore. Why? Because you have just too many letters in one word. You may go for like infinitely long. You don't really get to like check all of the letters in one word to compare it to another word. Okay. Okay, so it's not a well ordering. Or say for example, if yeah, okay, so I explained this already, and now we get the theorem. Theorem, well ordering theorem. If A is a set, then there exists an order relation on A that is a well ordering. If A is a set, there exists an order relation on A that is a well ordering. And this is like so cool. And this is like also so crazy because we just show that we only know how to well order by hand like countably infinite sets, and we have no idea what to do with all kind of sets which are uncountable, and we also show that we don't know how to well order like real numbers, right? And still we know that there exists some kind of well ordering. How do we prove this theorem? This theorem actually follows and was proven by Zermelo in 1904. And it's actually pretty complex, so we're not gonna talk about it today. But it's basically, it's like made a math world super amazed, because it's such a weird fact, right? If you think about it, how do you even well order real numbers, right? There are like so many real numbers just on the interval from 0 to 1. You cannot even well order this part because there are just too many of them. Well, it's like, no, sorry, not like, say for example, oh, actually, yeah. So it's really hard to like well order, for example, the set that looks, for example, looks like, if I'll write, if I'll write a set that looks like 1 and then 0 0.9, 0 9, so what 0 0 9, 0 0 0 9, and stuff, right? And I'll never touch 0. So basically, you see that there is like no smaller element, and we have like infinitely many elements going on here. So we don't really know how to well order it. So we always get the smallest element in the subset, and so it's pretty amazing that we actually have a theorem to say that we have it. So what can possibly be wrong with such a powerful theorem? Well, it uses axiom of choice, and that's why it kind of gives us a strange result, which is also very powerful. So axiom of choice gives us weird results which are powerful. That's basically the main conclusion you get from this part of chapter 1. But it also gives us nice things, right? And the corollary of this is there is an uncountable well-ordered set. Okay, so and this theorem is like so powerful, we don't even like use it much in the textbook. What we're gonna use most of the time is there exists some uncountable well-orders, at least one of them, which is already a pretty powerful fact. Okay, so definition. Let X be a well-ordered set given U in X, let S alpha denote the set S alpha equals to all small x's, which are elements of the big set X, and all those x's are less than alpha. So it kind of looks like a cut, or it's also called a section of X by alpha. Why? Because say if you look at X, like say X is equals to like real numbers, you look at this line, right? You take some alpha and you take all things that are less than alpha, right? And so this you call a section, or I think it's called also that it can cut. I'm not really sure, but I think that's the name. Anyway, so those are pretty important for set theory. If you would take the reading seminar in set theory, or if you took them, you already saw them, and they are pretty useful. Okay, so now lemma 10.2. There exists a well-ordered set A. Well-ordered set A having a largest element this, such that the section S this of A by this is uncountable. countable, but every other section of A is countable. This lemma made me really puzzled, like, because it's such an unintuitive thing. Like, how can you like oh, is there anything happening in the chat? Let me look. Do you do the set series? Oh yeah, we did a couple of things about Axiom of Choice on set series seminars. If you're gonna join them in the fall or maybe later in the summer, then yeah, we probably gonna talk about it. And so yeah, this is such a puzzling lemma. Like, I still kind of don't believe it really, because basically it tells you like, so you have like cuts, like say SA, which are countable. Like, you can actually like numbers their elements, and then you just get like something that's just maybe slightly bigger, like A plus some X, and then suddenly it becomes uncountable. Where is that border between countable and uncountable? And that's really weird. Okay, so the proof of the lemma. Proof. What we have is that know that S omega is an uncountable, well-ordered set, every section of which is oh my god, sorry. I'm reading my notes from other paragraph. We begin with an uncountable, well-ordered set B. Okay. So we know it exists. It was a corollary of our theorem, right? So it's an uncountable but well-ordered set B. Okay. And now what we do is we take C to be a well-ordered set 1, 2, B. So C is basically a Cartesian product of this little set with B. And we use dictionary order. Then some section of C is uncountable. Well, it makes sense, right? Because say for example, if you just take 2 and let it run through like all B's possible, then this would be uncountable because you have number of B's to be uncountable, right? Okay, and because you have even more elements starting, for example, with 1 in there, like you're sure that this would be uncountable. Okay, so let this omega be the smallest element of C for which a section of C by omega is uncountable. And so what we're basically saying is we have we have some kind of like pairs, and we know that some sections, for example, sections that go by here, are uncountable, for example, right? Because we have uncountable number of stuff that goes before them, and so yeah, we know that section is uncountable. And then what we do is we take an omega, which is the smallest element of C, for which it's an uncountable element. And so we can just say, then let A consist of this section along with element omega, right? And yeah, that was all the proof. It was pretty short. It's still kind of a weird proof to me because say I don't really understand how can we like find like a smallest element omega for which it would be like the section the smallest element for which a section of C would be uncountable. Well, apparently you somehow can do that. And then basically when you just like smartly make this entire pairs is like the trick that we used in the the part 9, right? And I said that we're gonna come to that trick a lot of times, right? Wait, is there anything in the chat? Yeah, magic of existence proof in math. Okay, and so what we do after that is we take A to consist of this specific section, right? And yeah, that's just the how the proof ends. You took any uncountable order set B, you took a Cartesian product of it to make pairs, you made them in dictionary order, you took a section which is a like smallest kind of section for which something is uncountable, and you just took this section with this element and it worked. So that's the entire proof, and I hope we can like you can get used to this idea, because I still didn't. And so we're coming to the last theorem of this part of the chapter, theorem 10.3, and it basically says if A is a countable subset of S omega, then A has an upper bound in S omega. Okay, nice. So the proof follows. Let A be a countable subset of S omega. So we're saying A is a countable subset. Then for each element of A, the section SA is countable, right? Well, yeah, because we know that SA is actually a subset of A, and A is countable, so SA should be countable. So SA countable for every A and A. Nice. And therefore we have the union B. A SA. And we know that it's also countable. Okay, and so since S omega is uncountable, the set B is not all of S. So B is just a proper subset of, it's not equal. Okay, so then let X be a point in S omega, and X is not in B, and such should exist because it's a proper subset. Okay, then X is an upper bound for A. Okay, and though because basically what happens if X is not an upper bound of A, there should be some element A of A such that A is bigger than X, and thus X should belong in SA, so X belongs in B, so it's contradiction. Oops, I don't know how I cleared the, you can do this. I didn't know that. Okay, so what happens, what we just did is basically we took a specific countable subset of A. So we had A, we took a countable part of it, and what we did is we took a union of all of its sections. So we took sections like S, A, blah, 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 right? Oh, sorry. A is a subset of S omega. And we took all its sections, and then we took a union of all its sections, right? So those are all of its sections, and we took a union of them. But then, even though we took a union, we know that this union should be countable because it's a countable union of countable sets, so it should be countable. But this thing is uncountable, so it means that it has elements we didn't count, and so we take one of them, for example, and it's outside of here, and we know that because of the way we ordered it, it should be an upper bound. Okay, so does this make sense? Okay, it makes sense, Nadir. That's good, because it doesn't make sense to me. Okay, so how about we go into exercises? Okay, so show that every well-ordered set has the least upper bound property. Anybody wants to help me with that one? So A is well-ordered, then A has a least upper bound property. For people who don't know what is a least upper bound property, least upper bound property tells you if your set A is bounded, at least from like above, then it has the smallest upper bound. So, for example, what sets have the least upper bound property is like, say if I have integers, I have a set of integers like 1, 2, 3, and I know that like all kind of numbers are bigger than all of those numbers, so like 4, 5, 6, 7 are all bigger, so they are all upper bounds, but from them I have the least one, which is 4. But say the same logic wouldn't work with real numbers, right? Why? Because you, for example, can have a set which is like, I don't know, like from like 0, like 1/2, whatever, 1. And then you know that like a lot of numbers are bigger than all of that, like say 1.1, 1.09, 1.009, but like you can never get to the smallest one, right? That's just right above 1. And so that's why it doesn't have an LUB property. So, but now we're saying if A is a well-ordered set, if it's bounded above, it always has a lower upper bound property. Anybody want to help me out with that one? So basically what we have to prove is, you have your set A, which is well ordered. If there is any subset, for any subset of A, it always has a least upper bound in A. Say A is a least upper bound of B, and A is in A. Yay! Okay, so Nadir, tell us this thing. Take all the upper bounds of B that are in A, right? So like upper bounds of B which are elements of A, and this would be some kind of a subset of A, right? Call it U in A. And because it's an A, it's well ordered, and because it's well ordered, you can find the smallest element in there. So U has smallest element. So there is a smaller upper bound. Okay, nice. Thanks, Nadir. Then exercise 2. Oh, wait, give me a second. Do I want to do that? Exercise. Well, yeah, sure, why not? It's actually pretty similar. Shows that in a well-ordered set, every element except the largest, if one exists, has an immediate successor. Immediate successor is basically an element which is like bigger than the element that we have, and there is no elements in between that is bigger. So basically, if you have a set A, its immediate successor is an element B, such that A less than B, and there is no C, such that A, C, B. Here. Okay, so basically we're saying in some set A, which is well ordered, there is, for any element except for the largest, if it exists, every element of A is not largest, A has immediate successor. So A has like something that's like immediately larger than A. Let me know if you have any ideas. Oops. Hey guys, any ideas? Oh, sorry, I didn't look at the chat. The set of upper bounds has the smallest element. Yay! Okay, so Nadir gave us a solution. Nadir says, let us take a section SA as SA. So basically, we take all elements. Well, that's not a section because we also have to remove A. So let us take all elements including A and less than A and just remove them. So we only consider elements of A which are bigger than A. And so basically what we have is some subset B of A of those elements bigger than A. And because it's a well-ordered set, it has a smallest element. So there is an immediate successor to A, which is that smallest element from all the elements that are larger than A. Does this proof make sense? Because so far, like, Nadir is a person who gives us proofs, so I want to see if others get the idea of proofs. And it's fine if you don't. Please just let me know, because we can like stop and go over it again. Nadir's just like, because he saw stuff like that before. It's not like he's like a super genius. He just knows that stuff. So don't feel like stressed or whatever. Theodora, does the proof make sense?
Sorry, I lost you like 40 minutes ago, and I've been trying to get along to understand what's going on, but I'm lost at this point.
Okay, that's nice to know. Can you, like, next time you get lost, can you just like tell us immediately, because it would be just like so much easier to correct at the point when you get lost than 40 minutes later. Okay, can you recall a point at which you got lost?
Let me see. At some point at the well-ordering theorem, but I'll just rewatch the recording. At this point, I feel like I'm hopeless. So, yeah.
It's really fine. So basically, what we did so far is, I think that you basically probably got like the part about the choice axiom and stuff. So if you have a choice axiom, what you can do is you can prove from having that choice axiom that you can well order things. And we never proved why, because it's a very complicated proof. We just said that Zermelo in 1904 did that proof. So from choice axiom, you get that any set, even uncountably infinite set, can be well ordered. So we have this really powerful theorem that tells us any set can be well ordered. Any set and any subset of any set can have smallest element if we just rearrange them in some smart way. And we don't always know that smart way. And so basically what we did after that is we just had a corollary of the theorem. Is like, we said every set can be well ordered. And basically now, when we're doing this, we're just using the definition of well ordered, right? So basically, we're saying if A is well ordered, then any subset of A is well ordered, right? Because it makes sense. Because you just use the same ordering, and it's just small number of elements. So of course it's well ordered, right? So like, say if I can well order like 1, 2, 3, 4, 5, and make some kind of ordering for them, of course I can order everything except for 5. I can order a subset of it, right? Because you're just using the same ordering. Or I can get rid of 3 and I have 1 less than 2 less than 4. So for any subset of a well-ordered set, it would be well ordered, right? So that makes sense?
And now you're doing. I'm so sorry. So what are we doing in the problems now?
Okay, so basically what we're doing in problems is we're saying, for example, in the problem 1 that we just did, we're saying we have a well-ordered subset A. We want to show that it has a least upper bound property, which means that if we have any subset of A, say B, any subset, what we have is that the subset B always has an upper bound in A. So there is always some element A, which isn't big A, so that A is bigger, or bigger than any element X in the set B. So A is bigger than all the set B, right? So that's what we want to say. Well, of course, if B is a proper subset. Okay. And so what Nadir said us to do is, how about we go and be like, we take A minus, not A minus B. We take all sets of, Z set of all upper bounds. So to give you an example, we have a set A, which would be from 1 to 10. We take its subset B, which would be from 3 to 7. We have a set of upper bounds of B, which is 8, 9, 10. And we're saying B is a subset of A. A is well ordered. So well ordered means that every subset of A has a smaller element. That means that B is well ordered. So every subset of B has a smallest element. So B itself has a smallest element. So we take the smallest element in B, in this case we take 8, and say, so 8 is the smallest upper bound. Because B was a set of upper bounds, it's well ordered, we can take smallest element of it, so we have a smallest upper bound, right? So that's what we wanted to prove, and that's basically all. So it's not like really hard. You just have to remember that definition of well-ordered means that you can have a smallest element for any subset, and that's what we did. And for the 2A, what we're doing is we're saying we have A, which is a well-ordered set, and for any element of A, when A is not largest, not maximum, it always has an immediate successor. Immediate successor is an element B in A such that A is less than B, and there is no C such that A less than C less than B. So basically, B is like the next element right after A, like the one that's bigger A, but there is nothing in between them, right? So does that make sense?
Mhm.
Yep. And so we're just trying to use a property that A is well ordered to see why. And this is really similar to the first exercise. Do you want to try to solve it?
Okay.
By the way,
Mhm.
Dekan, Huye, Linhe, Asmain, are you guys doing well? Do you is everything clear so far? Ooh. Yeah, sorry. Dekan, Huye. Oh, you're saying it's axiom for real numbers, right? You mean the choice axiom or the well-ordered theorem? Oh, yeah, of course. So this least upper bound property works for any well-ordered set. We showed that any set can be well-ordered because by choice, axiom of choice, any set can have a choice function. So even
wait. Yeah. So this is something I think I should clarify. So well, for real numbers, the axiom of choice is true for some kind of order that you can define, but not for the usual orders. Yes. However, for the usual order we have for R, it has a least upper bound property. So which means the well-ordered property is stronger than the least upper bound property, which means the well-ordered property can conclude that the least upper bound property is true, but not vice versa. Okay.
So yeah, I remember when I was telling you the difference that like Z by this order is not well ordered, but if we come up with some kind of like smart order, then it would be well ordered. That's basically what Professor just said, is that it depends on what, like, ordering you have. But like, yeah, you can always find some smart ordering for your set so that it always has like a smaller element or a trace function. Okay, so any ideas for to A? And I think after we solve to A, it would be already time, so we're done. So yeah, the last problem, guys. Let me see in the chat. Problem to be. Oh no, we're doing to A again this year. Sorry, because I wanted to make sure that people got the idea. But you can do to B because you solved to A. Linhe, Zakat, Kuye, Chadora, anybody ask me like so you know how you solve the first exercise. The second A exercise is really similar. Like honestly, like it's basically just the same.
Okay, so I don't know. I'm really not sure if that's correct, but what I think about right now is like if you construct a set where like B is the smallest element, and then you go and then you construct a set where you have an element C which is more than B, and then you go back to C1, C2, C3, and so on. Eventually, you get to a point where you reach element A, and element A becomes the smallest element of the subset of the original well-ordered set, and the element Cn, which is I would honestly feel better if I can write this, but the element Cn, which comes right before A. Like the subsets, we have the subset is Cn, Cn minus 1, Cn minus 2, and so on to B, and then the next subset is B, Cn, Cn minus 1, and so on to B. So like Cn would be the immediate successor of B or something like that, or A.
Wait,
sorry,
I got confused a bit. Can you like? Do you want to draw it?
Yes, I would honestly prefer to. I cannot draw.
Oh, okay. So basically, you're saying, how about we construct a set?
Wait, I will write it in the chat. We have the well-ordered set, and then we have a subset which has its smallest element as B, and then from there we construct a subset which has like oh wait.
Oh, so you want to construct a set which starts with little b?
Which starts with like I'm lost.
Okay.
I'm sorry.
It's fine.
So,
okay. So,
anyway, I lost.
okay, Nadir has to leave, but Nadir solved the problem. So bye, Nadir. So basically, the solution to the problem, which is like really similar, like as I promised, if you have a well-ordered set and you have an element A, right? What you do is take a set B such that all of its elements are bigger than A, right? So basically, if that's your A, this is your element A, we take this part B, which is all bigger than A. And because B is a subset of A and way A is well ordered, then B is well ordered. And this means that B has the smallest element, say B. And because it's the smallest element, it's an immediate successor of A, because there cannot be any C in between them, because then C would be in set B and it would be smaller than B. So contradiction. So B is the immediate successor of A. Does it make sense?
Yeah, it basically looks like the smart version of what I was trying to say, but
Yay, nice. So you got the idea.
that's good. That looks really good.
Okay. I know at least 2 people got the idea of these 2 parts of chapter 1. That's really good. And that means that others will get the idea maybe the next seminar, like next lecture on Friday. And guys, if you didn't get anything, we'll post the recording. You can rewatch it. You can also like do exercises. Feel free to like, I don't know, photo an exercise and then just like send it into the group chat and be like, hey guys, I need help with that, because like we'll really like we'll be glad to help you. Like, and we'll live in an old kind of time zone, so at any given point of time there will be somebody not sleeping and able to help you. So I hope that I was trying to make the lecture clear. If I didn't, then I'm really sorry.